The real difficulty with this problem is that none of us have ever worked at a gravel processing plant. And what I mean by that is sorting out what they're talking about is the real challenge here. The good news is it only takes 3 or 4 minutes worth of computation to do parts A, B, C, and D. And the real challenge in this problem is understanding what it is that they're talking about. The solution from my perspective is to read over the introduction to the problem a few times just to make sense of the issues. And after I read through that, here's the model that I constructed. So there's some sort of factory, and we may as well put a smokestack on it, because what would a factory be without a couple of smokestacks? And what comes into the factory is unprocessed gravel, and it comes in at a rate g of t. Now I'm going to talk about that a little bit more in a minute. And it leaves, or is processed rather, at a rate of 100 tons per hour. So the setting for this problem is really understanding that this is an application of the fundamental theorem of calculus. And what we really have to do is understand what is playing the role of f double prime of x, f prime of x, and f of x. The key is in seeing that what g of t is a rate. This is not how much gravel has arrived. This is how fast the gravel is arriving. And so if we were to make our own version of this diagram that illustrates the fundamental theorem of calculus, then what normally fits in the role of f prime of x would actually be g of t, the rate at which unprocessed gravel arrives. Then the second derivative, f double prime of x, is filled by the role of g prime of t. And that begs the question, what happens when we integrate that rate? Well, that's really key to this problem. And what you need to understand is that if you integrate the rate that something is arriving, then your new function, your integral of this, is the amount of unprocessed gravel that has arrived as a function of time. And so we have this gravel that's coming in and it's gradually piling up. However, there's a further issue here, and that is it's also the case that gravel is being processed and therefore, if you will, leaving this pile. And so you could imagine another application of the fundamental theorem that looks more like this, okay? Where the rate becomes how much is entering minus how much is leaving. Then the question is, what's the integral of that? And this would be the size of the pile. So what's key is seeing that integrating just g of t tells you simply the total amount that has arrived as a function of time. But integrating g of t minus 100 tells you how much unprocessed gravel you have at any moment. With that, A, B, C, and D are pretty straightforward. A asks for g prime of 5. Well, first of all, this is a calculator problem, and so we've already entered in all the various things that we're going to need. So we've put in y1 as the g of t, and then done the calculations that are required in this problem. The first calculation asks us to find g prime of the function at t equals 5. So we get that g of t equals negative 24.5875. Let's put that in. And it is the rate that the rate is changing. It's a second derivative, okay? So, which we interpret as the rate of unprocessed gravel entering is itself decreasing at a rate of 24.5875. I'm going to just emphasize that we're talking about the rate itself decreasing. Now the rate is in tons per hour, and so the rate that it's decreasing is in tons per hour, or tons per hour squared. B, total amount of unprocessed gravel. So that's going to be the integral from 0 to 8 of g of t dt. Again, I've done that calculation. And remember, the emphasis is to put in the formula once and then reference it in each of the successive parts of the question that make reference to it. So here I've done fn int from 0 to 8 of that function. And we get 825.5510. Tons of unprocessed gravel. The units, of course, are tons. That's probably redundant. We don't need to say that, but I want to point out again that the three rates were, or the two rates and the integral that we're talking about is tons per hour squared, tons per hour, and tons, because we're integrating with respect to time each time, and the units of time are hours in the example. Now, at t equals 5, is the amount of this pile, is the size of this pile increasing or decreasing? And again, the pile grows not according to g of t, but according to g of t minus 100. Okay? So we write whether the amount of unprocessed gravel is increasing or decreasing. I'm just going to continue C up here. Depends on both g of t and the 100 tons per hour rates of change. G of 5 equals, again I've done that calculation, 98.1407 tons per hour. And and 98.1407 minus 100 is less than 0. Therefore, the amount of unprocessed gravel is decreasing. In Part D, the question as to whether the pile is growing or declining, and therefore whether it's reached a maximum or not, has to do with the derivative of the size of the pile. Okay? And since the derivative is gt minus 100, we're looking for places where gt minus 100 equals 0. We also need to check the endpoints, and we would need to check where the derivative doesn't exist, but gt minus 100 exists everywhere. So we're going to write gt minus 100 exists for all of z from 0 to 8. We only need check for maxima at the endpoints and where gt minus 100 equals 0. At endpoints, well, how are we going to find those endpoints? At t equals 0, we're told that we have 500 tons. At t equals 8, well, we have to start with 500, since that's our initial value. Plus, we have to add the integral from 0 to 8 of gt minus 100. Evaluating that numerically, let's do that calculation. So what do we need? We need 500, since that's our initial amount. And now we have to integrate from 0 to 8, y1 minus 100. And we have to do that with respect to the variable that we're using. In this case, we're using x for t. So we get 525.5510. We could have known that we were going to get that because of the fact that this integral from 0 to 8 of the negative 100 part is just going to be minus 800, but then we also added in the initial amount, 500. but it was worth going through. 525.5510. So now all that's left is to find where gt minus 100 equals 0. And so for that, we simply want to graph gt minus 100, or rather we can graph the gt function and the 100 function and find where they intersect. Let's see what kind of window we want. Time should go from 0 to 8, so I've made it go from -1 to 9. GT minus 100, I probably should graph from maybe -100 to, or let's say, I don't know, -150 is about the lowest it could possibly be, and +150 is, let's say, the highest it could be. So now let's graph that. And in the first 8 hours, this is the intersection point. So let's find that. Make that our left bound, or our first curve, yes. There's our second curve, yes. And our guess, we'll close in a little bit on it. We know it's somewhere right around there. So the intersection is at t equals 4.9234. Finally, at t equals 4.9234. So now to find out how much gravel is there at that time, let's go back and look at the equations that we have. Okay. What we want is 500 plus the integral of this from 0 to 4. What did we just say? 9234. So let's perform that calculation. Uh, 500 plus the integral. I'm using FNINT. And we're going to go from 0 to 4.9234. And our function is y1 minus 100. And we're using x as our dummy variable. We get 635.376.1. And so the maximum amount we choose between the initial value, the final value, and the value where the derivative is 0. And this is the most. That's the maximal amount.